join with the audio, expand my window, got my nice new Blu-ray, whatever they're called, glasses. So staring at this computer all day long, you know. Anyway, when we started the trimester, we started with geometry. We're getting to the end of the trimester. We're ending with geometry. Doing something we've done before, but as I told you at the beginning of our time together in this study, if you understand integration after your first course in calculus, you've come a long way, all right? Because most folks just work with it mechanically and really don't have a feel for the symbols that are involved in the calculations. So I'm hoping that your thought process has matured and that this video will mean more to you now. Believe it or not, we've really been talking about these concepts the entire term, but to have it all come together and to make some sense as to what's going on mathematically takes some marination. So let's have at it. And I haven't got anything really planned out here, so hopefully I can do justice to the cause. And of course, I don't have them. Do I have a marker? That's a good one. Yeah, I'm really prepared here. Yep, I got a good one. Do I have an eraser? Yes, I do. All right, so I'll be putting a lot of things on the board, and let's see if you can help me out here, figure out how to explain some things. So here we have the cube. I put it together, some tape here, and we're high tech, so we got a cube, and it's got volume. It's got 3 dimensions. It's got length, height, width, all right, and definitely volume. And so, I think I just added some volume to that box. So the question is, how do you write it symbolically? So we want to start there. Oh, what are you seeing? Ooh, that's a geometric shape. That's a geometric shape. There, that's better. That's a geometric shape. That's pretty thin. Wow. But I got a feeling there's some kind of dimension there. It might be really small. So what did I do? I increased the volume. With this, it's got to be volume. That's a new box, a little bigger than the old box. This must be the what? Difference in the volume. Okay, so give it to me. Pause the video. What do I write? What do I write? A little change in volume. How about if I start with this? dV, difference in the volumes. Think of it that way, that's fine. Comes from what? Ooh, that's a square. That's a square and that's a square. Looks like there's 3 squares of area. You know, x times x gives me area, but what gives it the volume? Ooh, that last dimension, that's pretty small. What do you think I should write? Pause video. 3x squared dx. Now we're going to do a little approximating here. I got more layers. Let's see, what have I got? I've got, must be here somewhere. Oh yeah, there's my first layer. There's my first layer, yep, right there. There's my second. That's second layer. Oh, yep, it's on there. That got a little bigger yet. Oh, you know what? I got 998 more. Let me go down and do it. And let me just do it really quickly, all right? So be right back with you. Oh, I'm done. Oh, God, that box got bigger. Now let's work with some easy numbers here, all right? I know this was thrown together earlier in the day. I had to go through a lot of science classrooms to find something that seemed appropriate. And what did I find? Color changing magic mug. Very good. All right, so I'm going to say that this is a 2v2v2 cube. And let's just say that this is a 3 cube. Very good. All right, so I guess if I did 1,000 of those, I went from this cube to this cube. I wonder what the difference in volume is. Oh, I know a 3 by 3 by 3 has 27 cubic units to it, and a 2 by 2 by 2 has 8. Looks like I added 19 cubic units of volume. And how did I do it? One layer at a time. Oh, you know, this is actually a Riemann sum. I started with what number? 2 by 2 by 2. So what's the area? Looks like there's 12 units of area. And I'm multiplying that by what? If I did 1,000 of them, then I guess from here to here, I got 1,000 rectangles. 3x squared. From 2, I'll build it up further. I'll make it 3 here. Right? And what I'm doing is I'm doing 1,000 of these 3x squared times 0.001. And what's that going to give me? I always like running a quiet soccer practice, no talk for 2 hours. It's amazing what you see what players can do when they stop talking and actually start looking around the field. Same thing. I'm just going to be quiet again. 3x squareds, dx. I just trapped a little bit of volume. How much? .012. But of course, when I put the next layer on, there's one. There's another one. I don't know if you can see this or not, but this is getting bigger here. And now it's just got a little longer. In other words, this just went up. My dimension is now up to this. And when I square that and multiply times 3, and then multiply times, so I got to do the 3x squared. I got to do the 3 times 2.001 squared times 0.001. I get that new layer of volume that I added to what? To 8. Remember, we started with 8, 2 by 2 by 2. So my new volume now, I did this on the calculator because I wasn't sure of the pattern. I know there's a pattern here. It's actually an increase of 0.012, 0.012,003. 0.012, 0.012,003. And I invite you to see the patterns that emerge here. I haven't sorted it out yet, but doesn't mean I have to do it. Maybe you want to do it. Maybe you want to look at 2.002, and then you do 3 times 2.002 squared times 0.001, and we add another. That's another dV, by the way, that we're adding, right? Adding. You know what adding reminds me of? Kind of reminds. What's it remind you of? A symbol for addition that we've been working with. Of course, you know, each time I do this, I'm adding another layer of volume, What was that one? That one was 0.012024, 0.012024, 012. And then the next one, 2.003. If I do I'm adding 0.012, 0.012, 036, 027. Remember, so that's just, you know, another addition of a layer, you know, and each layer is bigger than the other. And eventually, if I keep doing that 1,000 times, I build the mug box. I do. So that's really a Riemann sum, where this is your partition, right? Your width, and each of these is the height, right? So, you know, when we did 2 left-hand rectangles, right? Didn't we talk about the width? Well, the widths now are dx widths. And this is the curve 3x squared. So let's put it all together here. Let's see, what do I want to say next? Oh yeah, let's add all that up. What do you think it's going to add up to? If you said 19, you'd be right. If I did 1,000 of these and then added it up, I mean, even if I just add up now, we got 12, 12, 12, and 12, that's 0.048. Right? We're close to 0.05, 0.05, and I'm on the lower rate end of that addition process. The layers up here are really going to start building up. Okay, so what is this mimicking? What is it mimicking? If you said the integral, and let's put this as an 8 plus 2, we'll put an x there for now. Let's do dummy variables. 3m squared dm, then when you made x3, that's what you're doing. And you're trying to see this as a rectangle, like a Riemann sum. That's integration. All right, and I think we're pretty darn good at this now. But I gave you a definite integral. I said from 2 to 3. So therefore, this is 8 plus, I want to go back to x's for you. That's what we work with in the math world. Well, I guess x in Arabic means something. So if you were to say 2x plus 5 equals, well, 2 times what plus 5 equals 11. 2 times something plus 5 equals 11. Algebra is born. All right. So where am I? Oh, yeah. Oh, yeah. If I keep adding up these layers, you're right. We're talking about the layering of the cubic process. And it looks like when you look at the cubic process, oh, it is changing faster when x's get bigger than when x's are smaller. In other words, if this box was half its size, smaller, then that layer that I put on has the same dx. It's got the same dx, but it's got bigger area. So that's why the slope of the tangent here isn't as steep as further up the curve. Okay? Because those volumes have a layering process that's bigger. All right, so this is actually good to do on a spreadsheet. I've done it in the past. Can I find where I put it on Google Drive? No. Would it be useful to see the printout of this and how close it comes to 19? Yeah. Oh my God, it's so close. I mean, the decimal accuracy is beautiful. But we don't need to do it in this fashion. We know the layering process came from this. And we're going to do 2 and 3, and we're going to go 8 plus parentheses minus parentheses. Can you see that? Barely. And we're going to drop that 3 and we're going to get 27. We're going to drop that 9. 8, 3 cubes. So used to doing quadratics. And that's 19 right there. There's my change of 19 added to the 8. 19 and 8. Oh, yeah. Gets me to 27. So that was the net change. Net change in volume. And the first fundamental theorem is, can you see up top here? Can you see over here to the right? Yes, first fundamental theorem is the area under the layering process. You can think of this little fx dx as the layering process. From A to B gives us the geometric shape that comes from that layering process, and it doesn't have to be a pretty one. It can be a pottery. It can be anything, because this is simply layering process that we're capturing graphically. Fx dx, f of b minus f of a, that is called net change in a table. So what's the net change in the cubic table? The net change in the cubic table from 2 to 3, 8, 27, a net change of, well, I suppose I'm looking backwards, 19 cubic units. And there you have it. And I hope that was a better job than what we did at the start of class. Parents weekend, parents coming in, trying to get breakout rooms, kind of hectic. So I decided I'd do it again. And who knows if you're going to watch it. I'm going to ask you to. I hope you do. All right. So I'm going to end the video.